Okay, can you hear me like this? It's okay? Oh, it's very inconvenient. Okay, can I open and close? How are you? Okay, let me present myself. My name is Natalia Panikashvili, and I'm doing postdoc at University of Michigan. And I'm experimentalist. I work already 10 years for Atlas Detector. And during my PhD, I also participated in the zero experiment. And if you have any questions which is related to the Atlas experiment or how to be experimentalist, you in principle can ask me questions after lecture anytime convenient for you. So, today I'm going to talk about particle physics toolbox, which is very important for us. Okay, how I move it? Okay, like this. So, today's presentation includes how experimental particle physics is a work, prototypical example, and then I will give many different examples. Then we will learn how particles interact with the matter, footprints, discrimination, and triggers. And then it will be good, in the end of the lecture, we will understand how the fact that we connect dots in the gas help us to understand the structure of the universe. So if we understand this point, it means that it was a successful lecture. Okay, so particle physics is reductionist. What does it mean? It means that in order to understand very complicated problem, in order to understand the particle physics or structure of some complicated problem, we would like to understand the small details, the small components, and also interaction between small components. So what actually we are doing? We break or open matter. We see what primary parts lie within. We observe how they interact, and we model the underlying structure. Okay, in the high energy particle physics, we adopt very sophisticated methods, very sophisticated. So first of all, we wrap up particles to the high velocities. We smack them into each other, and then we see what emerges. So this is more or less what we are doing. And then, to attempt this with subatomical particles, experimentalists work very, very hard because beyond day-to-day human scale in time and space. We must extend our sense with the specialized instruments and techniques, and these compromise the contents of our toolbox. So, how do we naturally observe our world? This is what happens. And this is actually applies to everything, right? So we always have a target. Okay, and we always have a source. And we have a detector. And if you don't like this detector, we can check. We can try this detector. Okay, what else we need? We need a probe, and we have also scattered rays. And then particle physics experimentalists emulate this process, and let's see what we have. So this is a particle physics experimental model. So we have a source, exactly the same. We have a probe, we have a target, we have emerging rays, and then we have, finally, detector. By the way, I put here the zero detector. I mentioned in the beginning that this I participated in the zero experiment, and what I did, I measured the lifetime of the hadrons. By the way, do you know what is a hadrons? And once I say B hadrons, it's what?
Hadrons B?
Yes, okay, good. And so I measured the lifetime of B sub D. So what is a B sub D?
What?
B sub D. What is the structure of the B sub D?
So B is metal with D.
Exactly. So I measured the lifetime of this d particle and also lifetime of lambda d baryon. So what is the difference between mesons and baryons? Good, you know a lot. Excellent. So I measured the lifetime of mesons, lambda d sub d meson and lambda d baryon, and we try to understand the difference, if there is any difference between baryons and mesons. Therefore, I put here the zero detector. Okay, good. Let's see what we have. So sometimes we wish to characterize a target, but it's not our job. It's a job of material science. We study the probe-target interaction, and this is in principle what we are doing in the particle physics. And we investigate the source and or the probe. It's astrophysics. So in all cases, we want to measure attributes of the emerging radiation. So what we want to measure is the mass, electrical charge, momentum, energy, multiplicity, and sometimes angular distribution. And this task of the particle detector. So our toolbox enables all facets of this model. We have a radiation producing sources. So actually I put all answers here. It's a radioisotope or cosmic rays or particle accelerators. Then we have a target. It can be fixed, stationary targets or colliding beams. Detectors, so we have many different types of detectors depending on what we would like to detect. For example, calorimeters, tracking spectrometers, we will talk about it. And data acquisition, it's the triggers, signal processing, and computer plus software. So let me start with the death of the plum pudding. Do you know, by the way, what it is, why, how it's related to the particle physics?
First, they thought that atoms like a plum pudding, that plums are inside.
Excellent, yes, exactly. Therefore, we talk about the death of the plum pudding because in the beginning, in 1909, scientists thought that this is an atomic model was known as a plum pudding, and they said, okay, this is what we have. This is our atom, right? Positively charged atomic mass, and then we have charged electrons. And then you know that Rutherford and Geiger asked student Marsden to investigate the penetration of the heavy alpha rays through the same gold foil targets, and let's see what happened. So they expected, because they saw that we have this pudding, right? So they expected to see small deflection of the alphas as they barrel through the ultra-thin foil. So this is what we expect, right? And let's see what happens. What happens is that Marsden instead observes many large angle scatters or ricochet. Okay? And from the observed scattering angles, Rutherford calculate all positive charge mass is concentrated in the atomic center in volume of diameter 1/10,000 of the atom. And this was the birth of the nucleon. And let me show you. So this is actually was very simple experiment, but it's important for us because it was the first target experiment. So let's see what we have. We have a source. In this case, it's an isotope, and we have a probe. It's an alpha particle. We have a target, the gold foil, and then we have a detector. It was a scintillation view screen, and we also talk about it. What tools did Marsden use? I already said the first tool is a probe, alpha beam emitted from the alpha sample of radium. The second tool, the detector. It was, oh my God, this is very complicated word. I don't know how to pronounce it, but this is a name. So this is actually a name for this screen, spinsariscope. And the third tool is a data acquisition system, which was very complicated and sophisticated at the time. So students equipped with dark adaptive eyes, pen, logbook, and a ruler. So another example of the scattering model is a cosmic ray. And here I just would like to mention that Vickers has observed cosmic rays, and actually he came to the conclusion that it came from the outer space. I don't want to talk about this experiment. I just would like to show you what he in principle saw, that we have a source. Okay, now we are talking about this our model, right? We have a source, it's a supernova. Then we have a probe with nucleus. We have a target, this is Earth's atmosphere. And this is emerging rays, cosmic ray shower. So this is actually what happens, and this is what we see in cosmic rays. And this is the cosmic ray detectors. We have a different type of detectors. We have a balloon. We have detectors at Earth on the surface, and we have also detectors on the ground cover. Okay, so the only way to know what happens in the probe-target interaction is to observe and measure everything that emerges. And we will now examine how different particle species leave their imprint, and then we can construct instruments to detect their passage or tracks. Okay, but first of all, we would like to understand the match detection methods. We would like to match the detection methods to radiation type. So let's see which kind of radiation type we have. So first of all, it's the electron-positron. So what we know about this particle is a charged particle, right? Very simple. They leave ionization tracks. They initiate electromagnetic cascades. They dump their energy in solid and liquid media. What about gamma photons we know? We know that high energetic photons do exactly the same as electrons, except what? What is the difference between photon and electron in all these lists? Any idea? What? I cannot hear you.
Charge?
Exactly. Yeah. So, because it's not charged particle, right, so we don't have this ionization track. Let's see what happens with the muons. So muons is also charged particle, therefore we expect that we do have a track. Now it's a very penetrating small energy loss along their trajectory, and as I already said, they leave ionization tracks. What about charged hadrons, pions? They leave ionization trails, initiate hadronic cascades, dump their energy in solid or liquid media. Sorry. Yes, and then, so particles with electric charge, we have two important things. The first one, they interact with atomic electrodes in matter and leave ionization trail. This is very basic, very simple principle, but very important for high energy physics experiments. And the second thing, that they pass in magnetic field curves according to their mass, speed, and direction. So these two basic principles. And then let's see the charge particle trajectory curves in perpendicular magnetic field. So what happens? So we have a particle, let me show you. This is a particle. This particle has a charge, mass, and velocity. So let's see what happens with the particle. It passes through detector, pass back, I don't know why. And then what actually we measure sagitta. Okay, because magnetic field, we have a perpendicular magnetic field, and this is what we measure. And we can do it, right? Because we know we have a track, so we can measure this. Once we know sagitta, what we can do from the formula? What do you think? For example, I would like to know the energy of the muon or electron. So what we can, and we can measure the sagitta. So what we can learn from sagitta for muon? Velocity. Of course, this is what we would like to measure. What we would like to know about particle. We know mass because we know it's an electron. Okay, and we know sagitta. So it allows us to measure velocity or to measure momentum or energy of the particle. Okay, now how to measure energy of electrons or gammas? So first of all, it's a Bremsstrahlung. High energy electrons decelerate near nuclear and loses energy as photon radiation. So this is the first principle. And the second principle is a pair production. photon near nucleus spontaneously converts into electron-positron pair. The energy of gamma becomes mass of electron-positron according to this. And at high energy, both of these processes occur in the same amount of matter. And then we have this in the detector. Okay, so we have a Bremsstrahlung and we have this pair production. So this is, by the way, example for electron. Okay, so this is the electron or positron. They make shower in the massive calorimeter. They can also be seen as a tracking detector. Okay, so in principle here you can see two different types of the detector. First of all, one part of the detector where we can see the track of the electron, and second part of the second detector, we call it calorimeter. So here we can see this shower. And in a good calorimeter, all of the energy of incident particle is absorbed. Why we want it? Why we want that in the good calorimeter all energy should be absorbed? What's the reason? Any idea? Because we would like to do what? We want to
measure the energy leaving from the particle.
Exactly, yes. Because if it goes out, it means that we lose energy, right? So we really want to stop electron and to release all energy of electron inside the detector. Okay. Therefore, it should be some heavy material. Okay, and this is what happens with the photon. We talk about it, right? The difference between photons and electrons, it's more or less the same. In the calorimeters, the difference that we don't see the track in the tracker, okay, because it's not charged particles, but we do see this shower in the calorimeter. Now, what happens with the muons? So fast muons leave continuous trail of ionization, losing a fraction of the energy as they pass through. What else? Protons, pions, kaons initiate hadronic cascades. They look like electron showers, but more spread out. Okay? And this is what we can see in the detector. And this is a neutrino. Okay, escape detector. But in principle, we can measure it. We can also indirectly measure, say that we have neutrinos. Do you know about methods to measure neutrino or to say that we had neutrino?
The missing energy?
Exactly. You're really advanced. I think that it's...
Yeah. We just did a course in quantum field theory.
Okay. So we have two main principles of detector detection method. So the first one is it's scintillators, and the second one is the gas field counters. So with the scintillators, we can actually measure energy or time of flight, or it works as a trigger, you will see. And with the gas field counters, we measure tracking in magnetic field, momentum measurement, and particle identification. So let me start up. This is a very important point, by the way. So what is really measured with these methods? What actually we measure with the detectors? What we have as the output? It's actually written here, so you can read and say. We measure pulse and nothing but the pulse. So we measure hits with digits. This is what we have, right? So the pulse location, we know always. The pulse amplitudes, sometimes you know, sometimes you don't know, depends what you would like to do. The pulse event time also. Sometimes we know and sometimes we don't know.
So what's the difference between location and event time?
Location, it's event time. If, for example, you have a different events, okay, that you would like to separate between one event and the second event. So this is the timing. Okay, so all physics is reconstructed from the above basic data. So let's see how we do. So plastic scintillators and phototubes. Modern scintillators would form. So first of all, we measure energy deposition. We measure, I already actually mentioned about it, measure time of particles and measure location. How scintillators work. So passing charge excite molecules in plastic. As molecules they excite small fraction release optical energy, and this light propagates inside the plastic to the surface of the phototube. Okay? It's a very simple principle. And then we need a phototube. Okay, so we have a photons pass through detector, and then we would like to detect, to catch these photons. And this is what I wanted actually to demonstrate, that we do it with the phototubes. So you can see here, this is a photon, and then a phototube. So what happens in the phototube? So we actually start with the photons, and what we have at the end. Do you know?
Very large signal.
Yes, but which particles?
Electrons.
Electrons, yes. And which principle we use in the phototubes?
Sorry?
Which principle we use in the phototube? So from the photons we get electrons. Yes, exactly. It's clear for everybody, right? Okay. So phototubes, they record a light pulse from the scintillator, very sensitive to minute level of the light, huge amplification. They can see even a single photon. It means very good resolution, and produce signal very quickly. It's important for triggering because they are very quick and time of the flight. So what happens if we actually put them together? We take the scintillator and we take the phototube, okay? And then we have very good tool to perform the measurement. So again, let's repeat it. So we have a particle which passes through scintillator, and then it produces photons through the interaction with the molecules. We have a photon, they pass through scintillator, come to the phototube, and in the phototube, due to process photoelection, we have electrons and we can read the signal. The amplitude of the pulse is proportional to the light intensity, and the number of the photon is proportional to the energy lost by the passing particles. It means that we can measure energy loss of the particle. Okay, now how in principle we can separate between signal and noise using the simple scintillator, because we may have our signal but we also have a noise. What should be done? So we use discriminator. So not all pulses are made by passing particles. There are also noise sources. This is what I said. We use discriminator to clean up the noise. So what we do, if the pulse is larger than the discriminator threshold, so output is true, otherwise it's false. So it's a very basic principle. So, and here you can see the example. This is a noise pulse, and this is a signal pulse, okay? So we just put the threshold from the discriminator, which says, I don't accept this one, but I accept this one. Okay, very simple principle. So digital output pulse when the signal crosses threshold. And then, okay, let's say that we want to observe a specific particle and not spurious heat and passing from the specific direction or with some flight time. So what we should do? We do this by forming a trigger. A trigger is defined by the heat coincidence in the specific detectors within restricted time interval. So let me show you how it works. Okay? So we have, for example, we use two scintillators and two phototubes. Okay, then we have a different noise produced by I don't know what, and then we have something that we actually came from the certain location that we would like to detect. So we use actually these two overlapping heats make a trigger pulse, and we put because they came in the same coincidence window, and then actually we accept this event. So let me show you how we use this principle for cosmic ray telescope, but it's not only the cosmic ray telescope, we also use it. Okay, first of all, I explain the main principle, and then I will tell you where we use it. So we have here two scintillators. Okay, so this is the one scintillator, and this is the second scintillator. And we have a cosmic ray. Okay, we have a muon, for example, from the cosmic ray, which pass through two scintillators. And what we are doing, we have a top left signal, top right signal. Okay, so we have a signal in the left and in the right, and we open the coincidence for the left and right phototubes, signals, and we do the same for the bottom right and bottom left phototube. And finally, we open the coincidence windows for both, for top and bottom, and we can trigger this muon. So this is actually principle. It's very basic, very simple, and we use it, for example, in Atlas detector. When we build the trigger chambers, we wanted to check the efficiency of the trigger chambers, using cosmic muons. Okay, but first of all, in order to build the trigger, to build the efficiency map, we want to be sure that we have a muon. Okay, so we have a cosmic muon. So actually we have our detector, and then we put it scintillators up and scintillator on the bottom, and we use this principle in order to trigger muon, and then use this muon for efficiency test of different type of chambers. It was muon spectrometer chambers. Okay, and this is, by the way, I put here another example where we also use this main. Yes.
Sorry, could you go one step back?
Yes.
What closes the top coincidence window, for example? You open the coincidence window when the two signals coincide, but then when do you close it? How is it closed? Actually, it's a question to the audience. Oh, forgive me.
It's not for me, it's good.
Oh, shut up. Okay. Did everybody understand that? Look, this is important. If you don't understand, ask.
We didn't hear what you said.
Ah, good. So that's it. So when there is a coincidence, as you can see, there is a falling edge. What about at the end of the coincidence window? The signal rises again. Why?
3 nanoseconds.
All right, fixed time.
Yes.
Fixed time. It was a fixed time window.
Yeah.
Okay. Everything is clear here? So let me just show you another example where we use this principle. So this is actually an experiment where we try to see the neutrinos. So we have a cosmic neutrino. Okay, if, for example, I'm here, we don't know why we put this map here. No idea. Okay, so we have a cosmic muons from this direction, and then we have a cosmic muons from the opposite direction. But we may also have a neutrino, right? So neutrino interacts with protons and neutrons, and then we have a muons from the opposite direction. So once we use these scintillators, we actually can say from which direction muons came, from the cosmic sphere or from the neutrino from the opposite direction. Okay, so next point, how to measure time of flight of energetic particles. So modern electrons Galileo methods, very simple Galileo methods. First, start pulse opens electronic gate, current flows in the capacitor, stop pulse close gate, and measure voltage on the capacitor. So it's very simple, right? We don't have any questions here, and actually I also try to demonstrate what I just read here. And this is, so we started with something very simple, right? We started to talk about one scintillator, and then we added a phototube, and then we saw that in principle we can take two scintillators and already measure efficiency, or to check from which the direction came muon. And I would like to show you what we are doing in the sampling calorimeter. And this is very basic technology that we use, for example, in Atlas detector for calorimeter. So we have electromagnetic sampling calorimeter. This is the layers of scintillators and lead. So let me, the green one is a scintillator, and the gray one is a lead. So by the way, why we use lead? We already talked about it. This material, why? I mean, it's a very heavy material, and we already talked about it, because we would like to stop electrons, right? Because we would like to electron release all energy inside calorimeter. Okay? So what actually we are doing, we measure using this scintillator, we can and measure the energy deposition in the different steps, in the different places of the calorimeter. And then what happens? Then sum of phototube signals, we use the sum of phototube signals to measure energy of entering particles. So this is the basic principle which actually we use right now in electromagnetic calorimeters.
If you lose the energy that is deposited with the light in this case?
Sorry?
I guess you measure only the energy in the scintillator part, but isn't there also an energy deposit in the light part? And you cannot measure it in this case, right?
Do you have secret lead or something like this? Because I remember seeing in one of the experiments there was like glass that was extremely heavy because it's been made of lead. Is this what you have in this case?
In the Atlas detector, do you know, by the way, if in the Atlas we have lead? Yes, we do have it. And we have to take into account the material, of course. We have to calibrate our energy depending on the material. So if it's a lead, we have to calibrate it to the lead. If it's something, a different material, we have to calibrate it to the different material.
How do you know how much energy you've lost in light, or how big is the energy deposit in light?
We do experiment before, we do the test beam in advance in order to check what is the energy deposition in the lead. Okay, the next type that actually I mentioned, the next method that we use is the gas field drift tubes detectors. So this is again a simple example of this principle. So we have a tube. Sealed tube with the gas inside. It can be argon or a little bit CO2, and then we have an ultra-thin anode stretched along the axis, and then we have a high voltage of about 300 volts between anode wire and tube walls in order to produce a high voltage. And signal picked off anode. Let me show you how it works. So passing particle ionize the gas. So this is actually the tube. Okay, so you see the phi plane of the tube, and here you see the wire. This is the tube. So passing particle ionized gas, electrons. Let me see if I have a movie here. No, I don't have. Electrons accelerate along electric field lines. Fast electrons ionize more atoms, and ensuing electrons avalanche produce big signal. Okay, so we can pack the drift tubes in the multi-tubes reading arrays. So okay, we see here tubes, and then we put tubes together. Why we want to do it? Any idea? So what we can do? We can, in principle, say if particle pass through one tube, okay, so we know the location where it happens, right? So if you put detector tubes together, so in principle we can really follow the trajectory of the particle, right? So this is what happens. Okay? For example, muon passes the tubes, and then we see the trajectory here. We have a segments here and segments here. So when a particle passes, the heat tubes produce signals. And as an integrated unit, these arrays record a particle track segment. So, and this is what happens. We have a one tube, and then we put tubes together, and then we already have a segment. And this is, we build the segments. This is the one small segment, this is the second segment. And then we build combined segment. Okay? Once we have a combined segment, it means that we already have direction, right? Because it's not only one point, it's already a line, and we know the direction of the particle. Okay, so here what I wanted to show, let me see. Okay, the time of the threshold crossing corresponds to electron drift time, and measures the drift time to get the distance of the track from the tube axis. Many possible tracks are tangent to the circle defined by the drift radius. And let me show you what happens again. From each tube drift type we obtain drift radius and drift circle. Okay, you can see it again. So we have a drift circle from each tube. And software algorithms find the one track tangent to the all drift circles. And now we have all measured track segments. This is how it works in Atlas. Okay, so what next? So we already saw that we took one tube, then we try to combine tube together, and then we can go further, right? So we can take these pieces of the tubes and put it like this. Okay, so why we want to do it? Let's see. Then we put, in addition to these tubes, we put trigger detectors, okay, some detectors. We put it here, let me show you. So we put it here, 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 here. Okay, then we have a drift tubes arrays. We put these detectors in the magnetic field, and let's see what happens. We have some particles that interact and move. And this is what we see. So now you understand the basic principle, right, of this, to put tubes together. Is in principle build detectors. Because now, if I know the position, if I have one tube, I have only one point. If I have several tubes, I know the second. We really would like to build the trajectory of the muon. Therefore, we need different detectors. Yes?
On the previous slide, you talked about how you could use the tangents to work out track within the tubes.
Mm-hmm.
But if you digitize the signal, surely you lose the information about where the tangents are. Because if you just take the pulse and change it to an on and off, how do you still work out where the tracks are going to?
It's a very good question. Any idea?
Did you guys get the question? Can you repeat the question? Repeat less London accent, please.
So if you digitize the signal and change it from a pulse shape into an on or an off, how are you still able to calculate the tangents through the circles which give you the tracks?
How you calculate?
Maybe we can discuss in the previous.
Yeah, sure. I didn't finish with this slide, but please.
Sorry. Yes, this one. The question is, reading out of the signal means collection of the electrons through the anode wire. So he's saying if you are reading out all the electrons and spitting out a number which is proportional to the deposited charge, then how do you understand the radius of the circle? That is the question, if I understood correctly. Yes? Did I paraphrase you correctly?
I think so.
Yeah.
But you don't have readout for each wire?
Of course we have.
So, electron passes sometime traveling.
Yes, very good. Did you get the hint?
Sorry?
Did you get the hint? She said something. Okay, so apart from charge, we also need to measure something else then.
Time.
Excuse me? Time as well. So we need to understand, we need to estimate when the charged particle has reached our detector. And we also need to measure the time of drift.
So how?
Yes.
So how do you like estimate going with the speed of light and take time between two wires and then?
Exactly, yes.
But again, it's not a perfect calculation, right? Because you have to know the track to know. Anyway. I think okay, to know the exact time between two entrance of two paths.
No, we measure the drift time. Okay, once we know the drift time, we measure drift circle and drift radius. In principle, we measure the drift radius and drift circle. But first of all, we need to measure the drift time.
So how do you measure the drift time? Just have a signal from the, like you get a peak in the signal. How do you know from that what drift time?
the first slide that you first introduced the drift tubes?
Yes, sure.
Yeah. Yes. Now, may I say my idea?
Yeah, sure, yeah.
Okay.
I'm waiting for your ideas.
Okay.
I'm not going to answer.
From here to here. When particle first comes from here, it starts ionizing, right? So it will take some time to take it here, come electron from here to here, and but the time that will pass for the electron here to here will be different, right? So from there, drift tube time calculation can be possible, and the exact time, exact path is found. It's my idea. At least I read like that.
Okay.
This kind of like isn't a track of the electron. I mean, when it goes to the center of the circle, I don't understand. In your explanation,
Line is the trajectory. Line is the actual path that particle goes through.
Yes, of course.
And it ionizes the gas inside it while it's passing through. And release the electrons. So electrons takes time to reach another.
Oh. Yes, I mean, I think this is more or less the right answer. What you said.
Okay, I also have a question. Volunteers. Why is the signal symmetric? The picture is very symmetric, right? No, the signal is not symmetric.
This one?
Yes. I mean, it peaks up very fast, then goes back to zero very slowly. But if you look at the picture, and whichever way it goes, it's going to go symmetric.
Surely it's because it comes in from one side of the tube. And so the particles are also traveling at the same speed as the electrons and the travel. And so they all group together, so there's a kind of wave of things coming across, and then they all go towards the. So when it gets to the middle, the back one first bunch of stuff comes in, there's like a lot at the beginning. That's what it was the good explanation.
No, I didn't understand what you said.
So,
I think our chemistry particles are driven.
Okay, I think the particle moves with speed of light, but the speed is much less than speed of light.
You would get this type of this shape also out of a scintillator signal. Now think according. Scintillator signal seen on a scope is also like.
Okay, so let's we answer these questions. Let's come back to the once we build detectors together. Okay, I'm here. So we put detectors in the magnetic field, and then we have muons. And then once we have muons, in principle, in the beginning we don't have muons, we only have hits, as I already said. Then we build the segments, okay? And once we have segments, what actually we are doing, we try to reconstruct combined segments, okay? For example, I take this combined segment and this combined segment, and once we have a number of the combined segments, we try to build tracks from these combined segments. Okay? And especially if we have a magnetic field, so we also can estimate the sagitta that I mentioned in the beginning, so we can actually calculate the curve and measure sagitta and to estimate momentum of how it works. Now, we also use trigger chambers. Any idea why we use trigger chambers here? Why we need to put the triggers in addition to these detectors? What do you think?
So that we don't read all the time, and we only read when there's trigger to go to be economic in terms of data and anything.
Exactly. Everybody understand this answer? Because it's very important. because we also have a noise, right? And we just don't want to spend our time to reconstruct event when we don't have real muon, right? So first of all, we would like to be sure that there is a muon there. Okay, so we have a coincidence. We have a hit in the coincidence window of this layer of the trigger and this layer of the trigger. Okay, we know that there is a muon, and then the next step, we try to spend our time and reconstruct muon. Okay, let me move. So this is actually more or less we have and what we learn. So we have a toolbox contents. We learn this one, electroscope, cosmic ray, plastic scintillator, discriminator, all these terms, and this is more or less our toolbox contents. And let me just summarize what we did. Actually, it's written here. You can read it after. And next, what we will do next in the next hour, or 45 minutes, I will try to talk a little bit about Atlas detector and show which results we have right now. And also, please ask me questions, and if we have, we can discuss it together. Okay, so give me 5 minutes. I will change my slides, and then we will start with the next 45 minutes. Is it okay?
Yes, sure.
Okay.